So this kind of problem has to do with the strain gauge. A strain gauge just measures how much deformation there has been in a particular object. In these problems, we just look at some kind of rectangle that's being stressed in the horizontal and vertical directions, and we just look at how much is being deformed. In a general case, I want to show you how we get our particular equation to use for these problems. Essentially, it just comes from the fact that we have our total x component, for example, of strain, and that's split up into x that comes from our sigma x. And remember, with Poisson's ratio, a stress in one direction does affect the other direction. Like if I stretch my piece of gum, it'll get thinner in the middle. So sigma x, there's also a component that comes from sigma y. So I can use this formula here, and I can substitute in Poisson's ratio in order to make my equation look like this. Then I go through, I replace my strains with stresses using Hooke's law, and I get an equation that looks like this. This is still our epsilon x. If I have that for both the x and the y directions, I can solve a system of equations to solve for sigma x and sigma y. That's the exact formula that we use for these types of problems. We just use it in different ways. In this particular case, we're given a particular strain and our material properties, and we have to solve for sigma x and sigma y. I have my formulas pre-written. These are kind of a plug and chug type of problem. Once we find the formula, we're good to go. I have sigma x equals E was 100 megapascals. Instead of writing megapascals, I'm going to write this as times 10 to the 6 pascals. It keeps my units more consistent. And I have the strain in the x direction, plus my Poisson's ratio is 0.1. That's my epsilon y, negative 0.01, divided by 1 minus 0.1 quantity squared. So I'm going to put that in my calculator, and I get 909,090 newtons, or in other words, 909 kilonewtons. Let's see what happens with our sigma y. We have the same E. Now we have our sigma y where our sigma x was, so it's negative 0.01 plus our Poisson's ratio times epsilon x. And our denominator is still the same. So I'll make those changes in my calculator, and it comes out to be the negative of exactly what we had for sigma x. Now let's see if this makes sense. Let's check for reasonability. So if I have my rectangular plate, it doesn't matter what size or shape it is, we're just looking at strain. It's just a ratio of how much it elongates. So if it got bigger, a positive strain means that it got bigger in the x direction, and our epsilon y is negative, so it gets smaller. Let's see, does it make sense that my sigma y would be negative, compressive? That checks out, that makes sense. It'd be pushing it in, it would make it smaller. Our new shape looks like this. Our sigma x is positive, so it's in tension. So again, it makes sense. It's getting longer this way, it's getting shorter this way, it's being compressed this way, and it's in tension that direction. So we can be confident with our answers, and that concludes this problem.